Okay, welcome back, everybody. Just a quick note, don't forget your exam number 3. All right, give yourself plenty of time. I think it closes at 10 p.m. Similar format, about the same number of questions, so multiple choice if you fill in. So I will tonight in the evening, if send a reminder out. Sometimes people get tied up and forget about it, so I'll send a reminder out if you haven't taken it yet. So, all right. Well, open the floor up. Any questions, comments, concerns? If not, I will continue with chapter 10. All right. And if I haven't moved the due dates for chapter 10, I will. Obviously, we're not going to get done with chapter 10 today, but we'll get through quite a bit of it. Okay, well, chapter 10, we're dealing here with chemical reactions. Now, we kind of introduced one of them already. We did when we did the acid-base reaction where we had the proton and hydroxide reaction. That was our first type of reaction that we're going to talk about. There's 6 reaction types that we're gonna work on. But what we're doing here, hopefully you can see what's going on, is we started off with the atoms. Okay, we kind of learned about the atoms and how the electrons are all put together in their electron configuration. And then from the atoms, we learned about the physical properties as far as which are metals, which are non-metals. Then we learned about how some metals gain electrons, and excuse me, let me restate that, how metals lose electrons and non-metals gain electrons to form ions. We started in the last chapter putting them together with the correct number of ions to get the right formula. We also talked about how they are, how the structure is, Lewis dot structures, to learn something about the polarity of the molecule and the polarity of bonds. And we're kind of culminating, putting everything together. So now we're at the point where these compounds that we made, we're going to start reacting with each other to form these chemical reactions. Now, on top of that, we're also going to be learning how to what we call balance these chemical reactions, because the conservation of matter tells us that matter is neither created or destroyed. It's basically just turned around, just moved from one format to another form. Okay. And that is to say that if I, for example, know the total mass of my reactants, 100 grams of all my reactants, and I go through a reaction process, something happens at the end when I tally up the amount of products, they should end up with 100 grams of material. Okay, that is called the conservation of matter. Also along those ways is that if I start off with 10 atoms of carbon in some format as a reactant, as it goes through the reaction, I'm going to collect at the end as products, I'm still going to collect 10 atoms of carbon. They will be in different formats, different structures, but it'll still be carbon. There's an example that I used to do when we used to meet face to face. It is a little experiment, a little show and tell, but I'm going to try to describe it here. And what I would take is a what we call Erlenmeyer flask, kind of shaped like so. It's a flask, and this flask was placed on this balance so we can read its total weight. Now, in here, we would put a little bit of acetic acid, aka vinegar, okay, acetic acid. And then on top of here, we will put a little balloon, okay, a little balloon. And inside the balloon, we will put in some sodium bicarbonate, aka baking soda. Okay, here's the base. Here's the acid. Okay, And then we'll get a number and, weigh it. And it's just for argument's sake, just say it weighed 100 grams. So all right, everything, the balloon, the container, so on and so forth, 100 grams. Well, we would take this balloon and then move it up and cause the sodium carbonate to fall inside that container of acetic acid. Well, a reaction will occur. And one of the products here was carbon dioxide. The result is that that flask and that balloon would fill up. Here it is right here. All right. And we would have the reading here. And that balloon would fill up with the carbon dioxide that was collected. So it converted the bicarbonate to carbon dioxide in the balloon. You can see it, balloon get bigger. The important aspect about that was the weight was still 100 grams. Granted, after a period of time, the weight would change simply because our connection here was not 100% with respect to the balloon and the flask. But the point being that it would just fluctuate just a little bit. And that was a classic example of the conservation of matter. This carbonate, which is a form of an ionic compound, is converted to carbon dioxide, a covalent compound, and it's a gas, and we collect a totally different format. It's still carbon in there, just in a different form. But the total mass before and after was the same. Okay. All right. So, and again, this is a statement. If I start off with X number of carbon atoms in the beginning as reactants, I should get the same number of carbon atoms. What we have here is we start adding, we have the equation and we start putting coefficients in front of the formulas. And we do that so that we can have a, quote, balanced chemical reaction. Now, the reason we want a balanced chemical reaction is because we're going to use these reactions to actually do some calculations down the road. Okay, I'll explain that here in a second. Now, so we're going to kind of talk about balancing chemical reactions. First of all, what generally happens is you're given a sentence of a chemical reaction. We need to convert that sentence into formulas and then write out the chemical reaction. When we're dealing with ionic compounds, step number one, like we did before, is we write those ionic compounds as ions first. We do that so we can make sure that we put them together with the right number of cations and anions, so they add up to 0. Then once we do that, we do what we call balancing. We put a coefficient in front of the formula. And so we might get up, hypothetically, we got an A plus B, maybe reacting to form, I don't know, something like AB. And maybe to balance things out, I got to put a 2 there and a 2 there. Maybe it's B, a diatomic B. While you can see here by putting coefficients up front that we have a balanced chemical reaction. We've got 2 A's on the left, 2 A's on the right. We got 2 B's on the left and 2 B's on the right. So we have a balanced chemical reaction. These coefficients are ratios that we're going to utilize, and I'll show you some examples here in a bit to do some hypothetical calculations. All right. So here we have a reaction. And this is a good example of what we call is one of the types of reactions, which you'll see here in a bit. But if we take, it could be written out in words. It could say hydrogen gas in the presence of oxygen reacts to form water. Okay. So we would take that verbiage, if you will, and convert that to a chemical reaction and say, okay, hydrogen gas, and this is where you need to remember all the diatomics. There's only 7 of them, the elements that are diatomics. We need to remember the physical state of some of the elements, whether there be a solid, liquid, or a gas, okay? And so that's a refresher. You might go back and refresh your memory. So hydrogen gas in the presence of oxygen reacts, okay? Or you can say reacts or gives or yields water, H2O, okay? Now, all of them are in the gas phase, so I won't include that. But notice here that we don't, at the way I wrote it, it's not a balanced chemical equation. So we have to balance it. So for some of the reactions that we're going to talk about, it's basically a trial and error. Not all of them. They're simple enough reactions that they're not that complicated and sophisticated that we can't balance them by trial and error, meaning we put a number here and see if it balances out. Doesn't work, we take that out, put a different number in. For some of these reactions, we do that. The other reactions that we're going to talk about, no, that's not the case. We have a systematic approach to balance these. But some of them, I do say, I don't say all of them, but at least less than a third of them, we got to do a little trial and error. So we have two hydrogens here on the left-hand side, two hydrogens on the right-hand side. So those are balanced. The hydrogens are balanced. All right. On the left-hand side, we have two oxygens, but on the right-hand side, we have one oxygen. So to balance those, what we do is we put A2. Let me change the color here so you can see. We put a 2 in front of water. Okay. So putting the 2 in front of water tells us we have 2 molecules of water. Okay. Which balances out the oxygens on the left-hand side. But in doing that, it increased the number of hydrogens. Well, no problem. Okay, now we got 4 hydrogens. Well, we go back to the reactant side, and we can correct that by putting a 2 in front of H2, which now we have 4 hydrogens on the left, 4 hydrogens on the right, 2 oxygens on the left, 2 oxygens on the right. And so now we have a balanced chemical reaction. And the ratio between the reactants is a 2 to 1. It's understood that there's a 1 in front of O2 there. We don't have to write a 2, but it's understood to be a 1, just like in mathematics. So that ratio between hydrogen and oxygen is a 2 to 1. That's an important ratio. We're going to use that information down the road here, all right? Here's a drawing on that to show you how balanced they are. The gray out circles represent the hydrogen. Notice there's 4 of them on the left-hand side, and there's 4 on the right-hand side. They're in the form of water, but still hydrogen, okay? Same is true with oxygen. We got 2 of them, diatomic oxygen on the left-hand side, and then 2 oxygen atoms on the right-hand side. So we have a balanced chemical reaction. As I was mentioning about the ratio, if we look at the reactants, a hydrogen to oxygen, it's a 2 to 1 ratio. Now, this is going to bring back memories when we were doing the conversion factors. And back then I said, hey, remember the system because we're going to use it again. And here we are. Okay. So we have the ratio between hydrogen and oxygen, which is a 2 to 1. Okay. We can write it in that manner, or we can invert it and write it in the manner we got oxygen on the numerator and hydrogen in the denominator. Okay. And that's the relationship between the hydrogen and the oxygen. But we also have a relationship between the oxygen and the water, which is the 1 to 2, and the hydrogen and the water, which is a 2 to 2 ratio. Okay, each one has 2 ratios that you can set up. There's a total of 2, 4, 6 ratios in this reaction relating the reactants with the products and then the reactants with each other. Now, why do we need to know that? Because just like we use these conversion factors, these factors in ratio form, we're going to use these to do calculations. We can, for example, I erased that by accident, don't want to do that. Let's say we have the 2H2 and O2 ratio. And let's say, for example, we need to make 10 grams of, use 10 grams of H2. The question may be, well, how many grams of O2 do we need? Okay. And so, or a better way to look at this is, if I have 10 hydrogen molecules, how many molecules of oxygen do I need? Okay. And so I write down like we did before, we write down what we're given, 10 molecules of hydrogen. You recall how we did that with respect to our conversion factors. And right away, you can see that the way I set up the ratio wouldn't work out. Why? Because my hydrogens don't cancel out. I need to erase that and use the other ratio of hydrogen in the numerator and oxygen in the denominator, right? Because when I multiply this out, I want my hydrogens to cancel. Then from the balanced chemical equation, I stick in the coefficients, which is 2 hydrogens and 1 oxygen. So if I start off with 10 hydrogen molecules, I would need 5 molecules of O2, okay? 5 molecules of O2. So that's how we're using these coefficients, okay? Coefficients to help us to get from point A to point B. Now let's take a look at these reactions, and here it could be given in words and saying that nitrogen in the presence of hydrogen reacts to form ammonia, okay? NH3. Everybody's in the gas phase. Now they're asking you here to balance these. Well, if you recall, remember, let's say we were trying to do iron 3 and oxide, put them together, and we had a dissimilar number of charges here, and we said, look for a common factor. And we decided, oh, the common number would be 6, right? So I need 2 of the iron 3s and 3 of the oxides, right? Our common number is 3. Well, we can apply that technique to these equations here to help us balance it. If you look here, we got 2 hydrogens on the left side, 3 on the right side. So we can use that similar, find a common number, which is 6, and say, okay, we need 3 hydrogens on the left and 2 on the right. Okay. And in doing that, now we have 2 nitrogens on the left, 2 on the right. We're good to go with the nitrogens. We got 6 hydrogens on the left and 6 on the right. So now we have a balanced chemical reaction. The ratio here is 1 nitrogen for 3 hydrogen molecules, which will produce 2 molecules of ammonia, okay? So to break that down, we can say, write it in this manner, and you can see we got NH3, NH3. All right, so you can see how it's balanced. So instead of writing each one individually, we just write the formula once and put the coefficient. All right, so there we go, balanced chemical equation. Here we have a scenario where we have hydrogen gas in the presence of bromine reacts to form hydrogen bromide, okay? Hydrogen bromide, which is an acid, HBr. Okay, so now we're gonna balance it. All right, well, we can just study it, look at it and say, okay, well, we got 2 hydrogens on the left, 2 Brs on the left, but we only got 1 of each on the right. So what if I just simply put a 2 in front of HBr? Okay. Go back and check it, hydrogen check, Brs check, we're good to go. We got a balanced chemical reaction. All right. Here we have carbon monoxide in the presence of oxygen reacts to give you carbon dioxide. All right, so a couple of ways to do this. I think the simplest way is notice that we have a total of 3 oxygens, 1 on carbon monoxide, 2 on oxygen molecule, and then on the right side we got 2. What if we even things up, get into an even number and put 2 in front of CO, okay? And that gives us a total of 4 oxygens on the left-hand side. Oh, well, to do that, we need to balance that, we need to put a 2 in front of carbon dioxide. That means that now we've got 4 oxygens total on the right-hand side. it kicks up our carbon, and by default, by putting that 2 in front of CO, it also kicked up my carbon, and so it looks like we are balanced there. Okay. And our ratio of carbon monoxide to oxygen is a 2-to-1 ratio. All right, now, when writing reactions from the words that you're given, make sure that you include the physical states. So refresh your memory on the physical states. When you're dealing with ionic compounds, remember the solubility rules play a factor here. So if they are ionic compounds and we're dealing with an aqueous solution, then if it's soluble, then we write the letters AQ, okay, like we did before earlier. Or if they're insoluble, we write the letter S, okay? We designate it as insoluble and it's a solid. Recall which elements are solid, which are liquid. There's only 2 elements that were solid, and about a dozen or so that were gas, and the rest were solid, okay? Remember, if necessary, well, you don't have to remember. Yeah, but this one you do, diatomic, okay? You remember which ones are diatomic. You might get something like written, the hydrogen in the presence of oxygen gives you water, right? So if you write it down like you read it, hydrogen in the presence of oxygen used to give you water. Well, we got a problem with this because we know that hydrogen is diatomic, okay? And we know that oxygen is also diatomic. So that would be correct to write it down as H2 and not hydrogen by itself. Okay, so we're going to remember the diatomic. All right, let's see. Subscriptions tells us, how many atoms in that molecule, whereas the coefficient tells us how many of those specific molecules we have in this reaction. All right, well, let's take a reaction written on words and let's break it down and write the formula for what is written, and then convert that to a chemical formula. And then from there, don't forget to include the physical states. And then also, then we do a balance. All right, so what we have here is sodium reacts with chlorine. Okay, so sodium, we're not talking about sodium chloride, sodium anything, just sodium. So it's got to be the element, right? Sodium by itself, which is a solid, reacts with are the key words for plus, okay? Then we have chlorine, I-N-E, chlorine, diatomic, Cl2, which is the gas, to produce is your keyword for the arrow, the reaction arrow. You may see to produce or yields or gives, so on and so forth. Then we have sodium chloride, which by the name tells you it's an ionic compound. So we need to first write it down as ions to verify that we put it together correctly. Okay, here's a physical state which is given to you. So we have sodium, which we know is in group 1A, and therefore when it becomes ionic, has a +1 charge. Chloride is in group 7A, so when it becomes a ion, or specifically an anion, it is a -1. Okay, so now you can see here that we can put them together simply as a 1-to-1 ratio. So we got NaCl, and we're given the fact that it is a solid. Okay, so now we have the base formula written down. The next step is to balance it. So we can simply see here, hopefully, that we have 2 chlorides on the left-hand side, but only 1 on the right-hand side, 1 sodium. Sodiums are good, but the chlorides are off. So what if we put a 2 in front of sodium chloride? That would take care of the chlorides. We're good to go there with the Cls. But in doing that, it kicked up the sodium from 1 to 2. No problem. We come over here to the left-hand side and put a 2 in front of sodium. And now we have a balanced chemical reaction, and we have the physical states, and we're good to go. Okay, here we write down what we were given from the words. Okay, we put in the physical states. Okay, and then we balance them out. Obviously, it wouldn't be formula-wise, it wouldn't be the NaCl2, right? Because that suggests that sodium is a +2, and just that wouldn't work. Why? Because sodium is in group 1 element. And being in group 1 element, metal specifically, it's only going to have a +1 charge. Okay? All right. Here's one. Sodium. Oh, excuse me, I got sodium in the brain. Aluminum reacts with bromine to produce solid aluminum bromide. All right, so we have aluminum, which you know is the element, specifically a solid. Reacts with is our plus. Okay? Bromine, like in chlorine, diatomic. It's also a liquid, right? Only one of the two liquids. To produce is our arrow. And then we have solid aluminum bromide. Okay, aluminum bromide. So we want to write them out first in ionic form. Aluminum always will give us a +3. It's a group 3 metal. Bromides, group 7, would have a -1. Okay, so to put these together, we're going to need 3 bromides for every one aluminum ion. So our formula becomes AlBr3, and we're told it's a solid. Okay, so now there's our basic formula. Now we've got to balance it. Okay, so in balancing it, we have a dissimilar situation. We got 2 Brs on the left, 3 on the right. Okay, no problem. We can use that little trick there. We're going to find a common number, which in this case looks like it's 6 again. So we put a 3 in front of Br, we got 6 on the left. Now we put a 2 in front of aluminum bromide, we got 6 Brs on the right. So the bromides are balanced, are good to go. But in doing so, it increased my aluminum quantity. So no problem. We just simply put a 2 in front of aluminum. And now we have a balanced chemical reaction of aluminum reacting with bromine to yield solid sodium bromide. Now, again, when we're doing this, keep eye on these ratios, because we will be using them down the road. And so I can write one ratio as so, or I can invert it with the bromine in the numerator and the 2 aluminums on there. And I can do the same for bromine and aluminum bromide, and the same for aluminum and aluminum bromide. Okay, so I got a total of 6 ratios. Which one I use depends on the question. If you recall, refresh your memory, when we're doing our conversion factors, you know, we write down what we're given. Then our first conversion factor, we're always going to have that unit in the denominator, because what we're given unit-wise, we want to cancel out to get us to whatever units we're looking for. And we're going to use the same principle here, okay, when we do these calculations. In fact, when we start doing calculations, you're going to end up with, as the case in the chapter of conversion factors, with at least 3 conversion factors to get from point A to point B. And in fact, how we do that, the common factor for all of these chemicals are the units of moles. Recall that when we were doing the pH, we said the units of molarity was moles per liter. Okay, we're going to talk about the units of mole. Moles is the common factor between reactants and products. I can't get from aluminum through to aluminum bromide directly. I have to go through the units of moles, okay? It's analogous to fruit, banana, orange, not connected, right? But if I have a factor that connects them, I can go from point A to point B, and that is, in that case, fruit, okay? Well, in chemistry, that interface is the unit of mole, M-O-L-E. Very important to get point A to point B. All right, so we first write the reaction with the proper formulas. Once you're done, now you can change the, once you're done now, you don't change the subscript. That's what it is. That's the formula for the compound. But we can add all the coefficients that we want. Now, let's say, for example, you're balancing this, and for whatever reason, you come up with a number that's twice that. So you, instead of 2, you get 4. Instead of 3, you get 6. And instead of 2 here, you get 4. And that in itself is a balanced chemical reaction. However, by convention, what you want to add is, I shouldn't say what you want to add. What you want to do is reduce those numbers to the lowest term, just like in mathematics. And every number there, 4, 6, and the 4 are divisible by 3. So you want to, if you end up with 4, 6, and 14, or for that matter, 8, 16, and 8, that's fine, but make sure you reduce those numbers to the lowest terms. Okay, and that is the proper, by convention, the proper way to present a balanced chemical reaction, and that is by the lowest coefficients that you have. Okay, lowest whole coefficients. And here are more ratios there that connect between the two reactants. Keep it in mind that the ratio also connects between reactants and product. All right, here's one reaction. This one says, write the reaction of phosphorus reacting with oxygen to form solid diphosphorus pentoxide. So currently it looks like we have a covalent reaction here, right? Because we got phosphorus, we got oxygen, they get together to form diphosphorus pentoxide, which is a covalent compound. Okay, so here we're not working with ions. Okay, so we're going to decipher from the formula given the actual formula we need. So we got phosphorus, okay, which is a solid, plus oxygen, which is again a gas, and it's diatomic, reacts to make solid diphosphorus pentoxide 1, like we did before. First, write the base formula, which is PNO, okay? And then we look at the prefixes, which is penta for oxide is 5, and di for phosphorus is 2. So now we have the formula P2O5, and it's a solid, okay? All right, now we got to balance it. And don't forget this stuff, don't present an equation that is not balanced, because that would be incorrect, right? And you can check by just very quickly seeing that, all right, I have, if I draw a line here, I got for phosphorus, I got 1. For oxygen, I got 2. For over here, phosphorus, I got 2. Oxygens, I got 5. So obviously nobody's balanced here at all. So what can I do here? Well, all right, so here we got a dissimilar situation, like the 2 and the 3, but in this case, it's a 2 and a 5. Okay, so you can use that same technique to even things up. So if I find a common number, which is 10, in this case, I can put a 5 there, okay? And I can put a 2 in front of P2O5. What that does is it brings my oxygens from 2 to 10, excuse me. And my oxygens go from 5 to 10. Okay, so they're good to go. Oxygens are good to go. The phosphorus is now, it went from 2 to 4. And I only got 1 here, so I can simply add a 4 in front of phosphorus. And now go back and check. I got 4 phosphorus, they check out, 10 oxygens, they check out. We got a balanced chemical reaction. So there's the formula, base formula. Then we come back and add the physical states, and then we just balance them out. And now we have the ratios. Again, we got 4 phosphorus to 5 oxygen. Now, something interesting about these reactions we've been working with, okay, is this. We have an element as reactants, and when they come together, they form a compound. Okay, so this is an example of a combination reaction. I just introduced to you another type of reaction. It's a combination, pretty self-explanatory with the name. I'm combining phosphorus and oxygen to form E2O5, okay? So now you have acid-base reaction, now you have combination reaction. And if you drove your vehicle today, you have the third type of reaction that we're going to talk about. That's called a combustion reaction, all right? Combustion, or if this past weekend you were doing the propane thing, it's a combustion reaction. All right, and in fact, all the ones we've been doing have been a combination. Here we have aluminum and bromine to form a compound. That's another example of a combination reaction, okay? All right, now, this one's a little bit more complicated. It looks complicated, but with anything, my goal is first break it down, okay? Break it down. So, you know, stepwise, attack it stepwise. This is by another type of reaction, which is related to the solubility table. So we haven't given up on the solubility table. There are some chemical reactions, you will get a specific name for it, that depending on the solubility of the products, that if they are insoluble, the products that is, then you have a positive reaction. And this is, I'll go ahead and give you the name. This type is called a double let me clean up my spelling. Double displacement reaction, RXN. Okay, so this is a third type. Combination reaction I just introduced. We've had an acid-base reaction. Now this is a double displacement reaction. We'll get a full summary of all these and you'll see a little better. All right, so we have this, looks very complicated, but what we're going to do is we're going to break everything down into ions first, okay? And we do that because we're going to recombine them with the correct number of ions to get you the correct number of the correct formula, okay? So let's take the first one. The first one says nickel, Roman number 3 sulfate, okay? So I'm going to write the ions, nickel 3. Let me change my color here. Nickel 3 tells us that we are working with nickel plus 3. Remember that? Sulfate. Well, I direct you to the polyatomic ion table. Okay, that is SO4 negative 2. Plus means, just like it sounds like, plus. Lead 2, so we're working with Pb plus 2, and then the nitrate, which is NO3 minus 1. Okay, again, I send you to the polyatomic ion table. Produces, that's your key word for the arrow, nickel 3, which we're still dealing with the same oxidation number, nickel 3 plus 3, nitrate, NO3 negative 1, and, which is the key word for plus, solid lead 2 sulfate. So we got Pb plus 2, and then we have sulfate, which is the negative 2, plus it's solid, so that tells us the physical state of the product, okay? Notice this aqueous solution. So the reactants, if we look those up, which we will, we'll find that all of them, the two reactants are aqueous and they're AQ, so we will put AQ. Now let's put them together with the correct ratio so we can write the formula. So we got a disparity here again with the +3 and the -2. So basically I'm going to need 2 nickels and 3 sulfates, right? So I got Ni parentheses SO4 subscript 3. That's nickel 3 sulfate. Plus lead, which is the +2 and the nitrate. So I need 2 nitrates. Pb parentheses NO3 2. And we need 2 nitrates here. Then I need nickel nitrate, which means I need 3 nitrates for every nickel +3. So I got Ni parentheses NO3 subscript 3 plus the lead sulfate that we can put together as a 1-to-1, okay? Because it's a +2 and a -2, so I can do PbSO4, okay? So that's AQ and AQ, okay? All right, well, if you look up the solubility of nitrates, you'll find that all nitrates are soluble. So the product here, the nickel nitrate, is also soluble, aqueous. The only thing that was not soluble is the lead 2 sulfate, okay? So note something, some observation. I got nickel sulfate, which is soluble. I put it together with lead nitrate, which is soluble, 2 clear solutions. I mix them together. They exchange partners. The nickel now attaches itself to the nitrate, giving you nickel nitrate, okay? Which by solubility rules show it to be soluble in aqueous solution. So I got an AQ there. The lead now interchanges with the sulfate to produce lead 2 sulfate, which based on the solubility rules is insoluble. So what we have here is a positive double displacement reaction. A positive double displacement reaction means that of the products made, okay, we're only concerned about the products. If one of them is insoluble as per the solubility rules, then we have a positive reaction. If both of the new products are insoluble, excuse me, and let me back up here. If both of the products are soluble, then we have no reaction. If at least one of them is insoluble, we have a positive reaction, okay? And here the lead sulfate is classified as insoluble. Therefore, we have a positive reaction. So we wrote the reaction based on what we were written here, okay? Now we got to balance it. So here's our pivot for balancing double displacement reaction. And our tidbit is this: follow the polyatomic ions, okay? All right, because notice on the left-hand side, we got 3 sulfates. On the right side, we got 1 sulfate. On the left side, we got 2 nitrates. And on the right side, we got 3 nitrates, okay? So you can pick one or the other, either follow the sulfates first or the nitrates. I'm gonna choose the nitrate, okay? I got a disparity number because I got 3 nitrates on the right-hand side. Change the color here. 3 nitrates on the right-hand side and 2 on the left-hand side. So I can put a 3, common number 6, right? So if I put a 3 in front of lead nitrate and I put a 2 in front of nickel nitrate, guess what? All of my nitrates are balanced. I got 6 nitrates on the right, 6 on the left, okay? Now, in doing that, my nickel went from 1, my lead went from 1 to 3. So I can go to the right side and put a 3 in front of lead sulfate. That kicks up my lead. So my lead is happy. Oh, you know what I did? I missed something here. Nobody caught that. Formula, this is why it's important. You put the right formula down. It's nickel 2 in here. Nickel 2, 2 nickels, all right? And so when I put the 3 here for the 3 leads, it balances my leads. I got 2 nickels by default, they're balanced. My sulfates, I have 3 on the left. Guess what? I got 3 on the right. So now I have a balanced chemical reaction. Pretty sophisticated, big reaction, but we broke it down in pieces, okay? You put them in ionic form first, put them together correctly. Don't lose what I just did there, because that definitely would throw a curve through the whole thing. Okay, but the formulas back. That's why it's so important. You put them together correctly with the correct subscripts. Then, with respect to balancing this type of reaction, follow the polyatomic ions as a unit. Don't try to break down 6 nitrogens over here, 10 oxygens over there. That just will complicate things. You're easier just to follow the packages, the individual polyatomic ions. All right, so here we have it. All right, so that is a classic example of a double displacement reaction. So what we're going to do now is we're going to give some generic examples of a chemical reaction. The first one, which we already talked about and made reference to, is called a combination reaction. In this scenario, you are reacting 2 elements to give you a compound. Okay, so a good classic example is if you, I'm not going to balance it. If you react hydrogen gas and oxygen, 2 elements, you make the compound H2O. Okay, H2O. So this will be balanced right there. 2. All right, combination reaction. Now, if I take a compound and I do something to it and I break it apart back to the elements, I have a decomposition. So I can use an example of water. I can do the same thing to water, meaning that I can take the water molecule and I can do electrolysis of water and I can break it back down to hydrogen gas plus oxygen. Okay. Right. So just breaking it back down to the elements. That's why it's so important to find water out in space. We can break it down and generate H2, which is a good fuel. And then more importantly, oxygen, which we as humans need. All right, so the next one is a combustion reaction. Here's the thing for Chem 130, okay, for us here, Chem 130, the only combustion reaction we're going to work with is the combustion of hydrocarbons. Hydrocarbons are compounds that are made up of nothing but hydrogen and carbon. So it's hydrocarbon, right? This X represents how many carbons and Y represents how many hydrogens. The simplest hydrocarbon is methane, where you got 1 carbon and 4 hydrogens, okay? Butane is a hydrocarbon. Your lighter using butane is a hydrocarbon. Propane is another example. Your vehicle has a lot of hydrocarbons. Yes, there's all kinds of other compounds in there, but it's basically mostly hydrocarbons. Now, when we could do a combustion reaction, and that's, a given thing, nothing burns without what? Oxygen. So oxygen is always a reactant, okay? And the products for the combustion of hydrocarbons are only carbon dioxide and water, okay? Yes, I know your vehicle, which burns hydrocarbons, also emits carbon monoxide. That's simply because the engine is not very efficient. Our burning or fuel is not efficient at all. And I believe somewhere in the order of 10, 20% efficiency is a pretty low efficiency. We can increase the efficiency by running extremely high temperatures, but then the metals can't withstand that for long time periods. Anyway, carbon dioxide and water are the only products that you get with the combustion of hydrocarbons. And the combustion of hydrocarbons requires oxygen. Okay, that's a reactant. With respect to the combustion, combination and decomposition, as far as balancing them, basically it's a trial and error technique for those two types of reactions. For combustion, we have a specific steps that you can follow, which we're going to do some examples of. Okay. All right. Acid-base reaction. We did this before. I'll clear this up. Okay, where we have or / neutralization reaction, because we have a covalent compound, which is an acid, associates to form the proton, reacting with an ionic compound, which produces hydroxide, which both of them react, neutralize each other to form water. And then we have the corresponding salt, whatever that salt may be, with the metal of the base and the anion, the nonmetal of the acid, okay? To balance these, the best thing is to follow the proton and the hydroxide. And balancing those first, the rest of the reaction balance falls into place by default, okay? Now we have the fifth type called a single replacement reaction. Now let's take a look at this. You have an elemental metal, okay, reacting with another metal that's in ionic form. So we have an element reacting with a ionic compound. And what happens is the metal that is in elemental form displaces the metal. A here represents the metal in ionic form. And so now what we created is a new ionic compound, MX. And then we generate the A that was ionic and put it back into the element, okay? Classic example of this is plating. If you plate jewelry, if you plate a lot of things, chrome plating, copper plating, all kinds of things, that's a type of reaction that you're taking the metal that's in ionic form and in solution, and you're exchanging it with another metal and causing that metal that was in ionic form to now go back to elemental form, okay? Now, how we determine this? Well, I'm glad you asked. How do we determine whether a reaction proceeds or not? Well, guess where I direct you to? The periodic table, okay? Right above the solubility rules, there's another little table called the activity series, okay? Notice you start off here on this side, you got lithium, and then on the other side, you have Au, which is gold. What this says is that lithium is more reactive than copper, then more reactive than barium, et cetera, until you get at the end of the road, which is gold. Gold is the most unreactive metal that there is, okay? And it's called a noble metal because of that. Gold that was buried thousands of years ago is still as shiny as the day it was buried. Doesn't mean that gold doesn't react. We can react to it, but it takes very harsh conditions to get it to react, okay? So we're going to use this table to determine that single replacement reaction, whether it proceeds or not, okay? And all that is reference to hydrogen. It's a relative scale relative to hydrogen, either in the form of hydrogen gas or in the form of water. And you ask, the way we do this, we're going to ask questions about the metals. And the answer will determine whether the reaction will proceed as written here, that this reaction is positive and will proceed, or we may get a result where you get no reaction, okay? So the single replacement reaction is governed by the activity series. We use that. And then finally, the one we just talked about was a double replacement reaction, okay? Where basically that subscript there, that doesn't mean it's one M or two M's. That just means it's two different types of metals here. Okay, so metal one exchange partners with metal two to generate M12, and then the other one is M2X. It's just a partner exchange. And then depending on the solubility rules for the products, it determines whether you have a positive reaction. If one of these products is insoluble, then you have a positive reaction. If both of the products are soluble, no reaction, okay? So we'll be using the solubility rules to determine that reaction with the products. We don't care about the reactants because we know the reactants are already soluble. You know, they're in the aqueous solution. Okay. All right, so some typical examples of combination reactions. You can see here that analogous to the A plus B to give you AB, we have phosphorus, okay? And we have oxygen to give us diphosphorus tetroxide, okay? We need to balance them. Well, we can put two oxygens here that balance off our oxygens there on the product side. And then there's two phosphorus, so we can put a 2 right here. So we've got two phosphorus here, 2 on the right, 2 on the left, 4 oxygens on the left, 4 on the right. So that's our balanced chemical reaction right there. And then note the ratio of reactants to products. Okay, 2 to 2 and 2 to 1 respectively. Okay, here's an example of, who can tell me the name of this species here? If you had to name that, what would you name it? Because it could be this reaction, instead of given to you as a reaction, it could be given to you in words. So you have to convert that into the formula. So what would I call this? Fe2O3. Obviously, it's iron oxide, right? But it's not a variable. It is a variable oxidation metal, so we have to figure out what oxidation state of the iron we're using. So which one do you guys think? Which iron are we using here? Any ideas? Remember that little trick about the subscripts to help you out? All right, well, that is iron 3. Okay. They're asking you here to balance it. Well, let's balance, and it's a decomposition. Notice we have a compound breaking it down to generate the elements, iron and oxygen. All right, so we got 3 oxygens here. We got 2 oxygens over here. Let's find a common number. Let's say we do 6 again. So we got 6 on the left, and now we got 6 on the right. So the oxygens are taken care of, okay? But in doing so, our iron content went up to 4, so no problem. Boom, put a 4 in front of Fe, and we have a balanced chemical reaction. Okay. All right. Now, combustion reaction. As I stated, with respect to us in Chem 130, the only combustion reaction we're going to work with are the combustion of hydrocarbons, okay, which are compounds that are made up of nothing but carbon and hydrogen. All right, so do you remember what is necessary for any combustion? You recall what I've stated, what you need for anything to burn. What is one of the reactants necessary? Any ideas? If you want to burn some trash, what do you need to burn it? It could be anything. What is the one key ingredient necessary for any combustion reaction to occur? All right, we got an answer. Let's see. Carbon? Ooh, not quite. Not quite. Okay, for anything to burn, be it carbon, even there are some non-carbon based burning, but you can get metals to burn. You can get magnesium metal to burn. And even that you need it to survive. What key ingredient do I need to survive? Which is the same key ingredient you need to burn anything. Oxygen, right? Thank you. Exactly. You need oxygen. And so the situation could be this. You could be given the problem, write the combustion reaction of propane gas. And that's how they give you. Well, the key is combustion, okay? The second key is the formula they give you. You may not know what the formula is, but recognize it is nothing but carbon and hydrogen. So you have a combustion reaction of a hydrocarbon. So for anything to burn, I need oxygen, okay? Anything. Next time you're out there, cooking got your barbecue or propane tank going on, if you shut down that air supply a little bit as far as the oxygen content or block it, it's not going to burn, okay? Any fire that you need to turn off, what are you trying to do? You're trying to get rid of the oxygen, okay? Now, for combustion reactions, what are the two products I stated are the only two products you get for any combustion reaction of a hydrocarbon? Remember what I stated? Any ideas? Well, one of them is pretty crucial because the more stuff we burn, the more of it goes in the atmosphere. And we have a hard time with it. Any idea what that is? There are only two products, okay? And these you gotta remember these. Carbon dioxide, and what was the other part? What do we got here? There you go. Thank you. Carbon dioxide, and you gotta remember the formula for that, CO2 plus water. Okay, so those are the two products you always going to get. And everybody here is in gas. Propane is a gas. Physical state, everybody's is a gas. Okay. Now, for the combustion of hydrocarbons, Now we have a systematic approach to balance these equations. This is down here at the bottom. This is a model of propane. Propane. We got 3 carbons there. And then we got the hydrogens bonded to the 3 carbons. And 3 carbons are bonded to each other. Now, step number 1, in the combustion of hydrocarbons, you balance the carbons first. Balance the carbons first, okay? So always look to the reactant side. You have 3 carbons on the left-hand side. On the right-hand side, the carbon exists in the form of carbon dioxide. So I simply put a 3 in front of carbon dioxide, okay? Step number 2, balance the hydrogens. Next. Okay. And generally you start at the left-hand side again. That's the hydrocarbon. It's got 8 hydrogens. Now, on the reactant side, the hydrogens are in the form of water. So I need 8. So if I put a 4 in front of H2O, guess what? My hydrogens are now taken care of. So my carbons are taken care of. My hydrogens are taken care of. Now, finally, at the end, balance the oxygens, okay? Now, here's the thing sometimes the students forget. Oxygen, no, you're always going to start off with just 1 molecule of oxygen on the left-hand side. Your oxygen is going to be in the form of carbon dioxide and in the form of water. So you got to count all of the oxygen. So you can see there's 6 oxygens in the form of carbon dioxide because we have 3 molecules of CO2. 3 times 2 is 6. Water, there's 4 molecules of water. Each one contains 1 oxygen. So we have 4 oxygen molecules coming in the form of water. So total, we have 10 oxygens. Okay, 10 oxygens in both carbon dioxide and water. So now we're going to go back to the reaction side, take that 10, divide it by 2, and stick it right in front of O2. Okay, so now we have 10 oxygens on the left-hand side. Okay, 3 carbons on the left-hand side, 8 hydrogens on the left-hand side, and on the right side, you have the same 3 carbons, 10 oxygens, and 8 hydrogens. Okay. Notice the ratio of propane to oxygen. You need 5 molecules of oxygen to burn 1 molecule of propane. And when these hydrocarbons get bigger in size, guess what? You need a lot more oxygen to burn that stuff off. And which then, can deplete over time. We do too much burning, can eventually deplete our oxygen content. And that's something, we hardly don't talk about, but we really something to think about. Coupled with that, for every molecule of hydrocarbon, you are creating 3 molecules of carbon dioxide. That carbon dioxide goes up into the atmosphere. Okay, it's not going to leave space, going to space because it's held in here on Earth as gravity, and eventually goes up to the upper atmosphere, and will act as a blanket and reflect the heat coming off the Earth back down to Earth. It's sort of like, we all know about the summers here. You go out to your car, you drive to school, to work, nice and cool, and then you come back to your car in the afternoon. Well, you open that door up, it's pretty hot. Okay, because all that heat that built up in the vehicle was being reflected back into the vehicle. And that's how the gases work up there. You reflect it back, temperature goes up. Anyway, key points as far as the combustion of hydrocarbons. 1, only those hydrocarbons which are made up of carbon and oxygen only we're going to work with. Second point is you require oxygen for it to burn. Okay. Third point, the only two products that you're gonna make from this combustion is carbon dioxide and water. And then to balance it, you balance the carbons first, then the hydrogens, then the oxygens, and everything falls in place. Okay. All right. Well, I tell you what, let me stop it here. We are 10:14. Okay, let's stop it here and we will continue on Thursday.